All right, let's look at some second order effects on the structure of molecules. First, let's talk about electronegativity. Electronegativity, again, is the ability of an atom in a bond to attract electrons to itself. And so basically this scale, fluorine is the highest with electronegativity of exactly 4. And so fluorine bound to any atom will attract electrons more strongly to itself. And how much more strongly they're attracted depends on the difference in the electronegativity. So the closest to fluorine is oxygen. And so fluorine is stronger than oxygen at attracting electrons, so it'll attract more than oxygen. But fluorine attached to something like boron will have a huge attraction for the electrons in the bond. So those bonds will be very polarized. Let's see how this affects structure. Electronegative atoms bonded to less electronegative central atom tend to draw electron density away from the central atom and lower repulsion. And so of this set, we have PF3, PCl3, and PBr3. And you notice there's a huge drop in electronegativity as we go from fluorine to chlorine, and then a smaller one as we go from chlorine to bromine. And so the idea here is fluorine attracts the electrons out onto the fluorines. That makes the bonds themselves less repulsive, and so we get angles that are closer to 90 degrees here. Yeah, another major effect here is size, and we have, let's compare, for example, this is called an arsine. This is arsenic attached to 3 hydrogens. And this is has the same structure as a phosphine. So it has a lone pair on arsenic and it has 3 hydrogens attached. This one has a lone pair on phosphorus that has 3 hydrogens attached. And notice when we go from pH3 to ASH3 that we get a decrease in the bond angle. Okay, so there's less hybridization that's going on here. As we go down these columns, there's less mixing of the s and the p orbitals. So the arsenic and the hydrogens are bonding much more just through a p orbital on arsenic and the s orbital on hydrogen. And then if we want to throw in also the effect of the electronegativity, we have that electronegativity effect here too among this set. Again, the fluorine, which has the electronegative, is the most electronegative atom, pulls the electron density away, and so it has a smaller bond angle compared to those. So here's all of this sort of given together. The relative steric demand of objects is different, and the amount of repulsion caused by the object will alter the arrangement of the atoms around the central atom. And so the smallest here is a long single bond polarized away from the central atom. So this is something like phosphorus and fluorine. And because this is electronegative, most of this electron density, or a lot of it, gets pulled out to the fluorine. And so if there's another one of these on the same central atom like we have right here, then these fluorines are not as repulsive for one another. And so this angle is smaller than 109.5. Okay, it shrinks because the fluorines aren't as repulsive for one another as the hydrogens are. Then we have a normal single bond, and a good old CH bond is a normal bond. It's kind of here in the middle. Here we have a multiple bond, so something like this right here. This is more repulsive than a normal single bond. And then a lone pair is the most repulsive, and you can think of it because it's so wide that it's taking a good chunk of the central atom. Remember again, the yellow one here is the central atom. And so if I have a lone pair and I were to have a single bond here, this lone pair is more repulsive than the single bond. Or if I had another lone pair, lone pair, lone pair, it would take up a whole lot of the surface of the central atom. And yeah, this is just some comparison. So these are all real molecules and the real data for them. Here, I want to draw your attention to the fact this is a carbon-carbon single bond, but this one is a double bond. And so this double bond is more repulsive than the single bonds. And so what happens is this ideal angle of 120 opens up to 121.8 here and here, and that also shrinks down the angle between the single bonds. Here we have double bonds in a lone pair, and again, this would be an ideal angle of 120. It shrinks down because the lone pair is more repulsive than the double bond. So here's the process that you want to do. Given a formula, predict the Lewis structure, figure out the number of electron domains. So this sulfur has 4 bonds in one lone pair, so it has 5 electron domains. This puts you into a trigonal bipyramidal structure. And ideally, the idealized structure has a 90-degree angle here, and then these angles are 120. But then you have to get sort of a second order structure, you have to go in and imagine that this is more repulsive than the bond pairs. And so everything actually gets pushed back away from the lone pair, and this angle opens up.